Hello, fellow students, and welcome to this lecture. Today we are going to talk about planar graphs and the chromatic number of a graph. So stick around and enjoy yourselves. I'm going to share the screen. And this is the problem that we have for today. As you can see, it is the same graph as in the last lecture, right? So we are going to continue working with this graph. The first question that we have is if it is a planar graph. And then if the answer is positive, we need to mark the regions in the graph. Okay, so first, let's define what is a planar graph. And it is the graph that can be drawn without overlapping edges. So to check this, first, we are going to see if it meets the needed condition, right? So before trying to draw it, first we check if it meets the condition needed, okay, but not sufficient to be planar. This means that if this condition is met, it could be planar, but it is not enough, right? There could be other conditions. But what we are sure about is that if this condition is not met, it is not planar. So this comes by the formula is 3r divided by 2 is less equal than m, and it's less equal than 3n minus 6. And in this case, n is the number of vertices of the graph, right? In this case, we have 6 vertices. M is the number of edges, and in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. And finally, we have R, where R is the number of regions, right? So we still don't know, right, the number of regions. So to calculate this, right, to calculate the number of regions, we use the Euler Formula. And this formula says that n minus m mass plus r is equals to, right? So if we leave r alone to the left, we have that r is equals to 2 minus n plus m, which gives a value of 2 minus 6 plus 9, right? Which is equals to 5 regions. Okay, so coming back to the first formula. Coming back to the first formula, right, which was something like this. We just need to write the values of the variables. R is 5, minus equals m, which is 9, less equals 3 by 6 minus 6, right? And at the end, this is 7.5 less equals 9 less equals 12, right? So the condition is met. As you can see, 7.5 is lower than 9, which is lower than 12. So it could be planar, right? It could be planar. So what we are going to do is to draw the graph in a way that the vertices doesn't cut, right? We are going to try to draw it. In my case, I know more or less which is, let's say, the final form of it. So I'm doing something like this, right? I'm putting all the nodes here, and then we have a link between 4 and 6, between 4 and 3, and between 4 and 2. Then we have another link between 6 and 1, 6 and 4, okay, 3 and 1, 1 and 5, 1 and 2, 2 and 5, and finally 3 and 2. Okay, so as you can see, it is planar, right? It is planar. The edges do not cut or overlap each other. And then we are going to draw the regions. So for instance, let's draw it in blue. This could be the first region. This could be the second. This could be the third. And this could be the fourth. And then remember that the outside of the graph is the fifth region, right? So this is exactly, right, what we got with the formula. Okay, so this is the answer to the first question. And now we are going to see the chromatic number, right? If it's possible to calculate the chromatic number. So first, we are going to start, okay, with the chromatic number. We are going to start with the upper bounds. And we have also some formula. So the first says that if the graph is connected, we have a formula that says that 1 is less equal than the chromatic number. Okay, let's call it key sub g. And it's less equal than the number of vertices. Right, so the first bound is that 1 is lower equal than key sub g, which is, oh, sorry, went to the next page, lower equals than key sub g, lower equals than 6. Then we continue, right? And we know that the chromatic number must be less equal than the maximum degree of the vertices plus 1. Right, so we need to calculate the maximum degree of the vertices of the graph. The degree of the vertices was the number of edges that are incident on that vertex, right? So for instance, for 4, we have a degree of 3, right? Because 3 edges are incident on that vertex. So we start to count, right? So this is degree of 3. This is a degree of 4 for 2. For 5 is a degree of 2. For 6 is a degree of 2. For 3 is a degree of 3. And for 1, there is a degree of 4. So we can say that the maximum degree of the vertices of the graph is equals to 4, right? So then the formula says that the chromatic number is lower equals than 5. Okay, so it's already, well, let's say 4 plus 1, okay? So, okay, we have come down to the number 4 for the chromatic number, but we also know that any planar graph is 4 colorable, right? That means that if the graph is planar, the chromatic number is lower and equals than 4. Okay, so this is the most we can get, right, with the knowledge that we have, the theoric knowledge that we have about graphs, right? So the upper bound is 4, right? The chromatic number must be equals or lower than 4. And we are going to see the lower bounds. For the lower bounds, we know that if there are cycles of even length, the graph is not too colored, right? This means that if we are even cycles, we cannot use only 2 colors to color the graph. Sorry, it's odd cycles, right? It's odd cycles. So we check if there are odd cycles, right? So for instance, here, let's think about this cycle, right? Which is odd. We have a cycle of length 3 here, right? If we use one color to color the vertex 1, then we need to use a different color for 2 and a different color for 5, right? So at least we will need 3 colors. Let's write the definition of chromatic number in fast, right? The chromatic number of a graph is the smallest number of colors needed to color the vertices of the graph so that no 2 adjacent vertices share the same color. Right, so you can see here how we cannot do it with only 2 colors, right? Because these 3 nodes are adjacent. So we will need 3 colors at least. So this is what happens with odd cycles. Doesn't matter if the length is 3, 5, 7, 9, right? It will always happen the same. We will always have this problem. Okay, so the answer is yes. We have the cycle 1, 2, 5, which is odd. So that means that G is not too colored, right? So that means that we need at least 3 colors, right, to color the graph. Like this, we arrive to the final bounds, which are that 3 is less equal than the chromatic number, which is less lower equal than 4, right? So the chromatic number must be between 3 and 4. So what we are going to do is we are going to color the graph according to the algorithm, to the coloring algorithm, to see which is the final number, right? So to color the graph, first we list the vertices ordered by degree, right? So we start by the vertices with the higher degree, which are the vertex 1, which degree is 4, then the vertex 2, which degree is 4, the vertex 3, which degree is 3, the vertex 4, which degree is 3, the vertex 5, which degree is 2, and the vertex 6, which degree is 2, right? So we have the vertices ordered, and we just start by the first one, right? So we start by the first one, we choose a color, and we color this vertex. So we color the vertex 1 in blue, right? And then we take the vertices that are not adjacent to 1, and we color them in the same color, right? So for instance, 4 is also colored in blue. Once that we have done this, we go for the next one, which is 2, and we are going to color 2 in red. So we color the vertex 2 in red, and the ones that are not adjacent, right, which is only 6. Six is the only vertex that is not adjacent to 2. And we go for the first one, for the next one, which is 3, and we color it in green. And 5 is not adjacent to 3, so we color it also in green. Okay, so this is the algorithm, and as you can see, we have used 3 colors to color the graph, right? So the chromatic number is 3, right? And this is the final answer to this exercise. Okay, so thank you very much for joining me today. I hope that you enjoyed the exercise. Anyway, if you have any question, please don't hesitate to contact me or to ask in the comments right behind the video, right? I will try to reply your questions. And as always, thank you very much for joining me today, and I hope to see you soon. Bye-bye.